Section: Introduction. In this section, we discuss modern computer vision and text models, which are often pre-trained on large datasets that capture much of the Internet's knowledge. While this has resulted in impressive capabilities, we are increasingly concerned that these models may rely on superficial, local information instead of engaging in deep reasoning. Evidence indicates that many models operate mainly through retrieval, acting as blurred versions of the Internet. They excel at interpolating within this encoded knowledge but struggle to understand the real world's complexity and logic. Currently, there are no rigorous benchmarks to evaluate a model's ability to perform global reasoning and multi-step problem-solving in visual tasks. Most existing visual benchmarks focus on tasks solvable with superficial cues and local features. Our goal is to address this gap by investigating whether current models can learn tasks that require deep, multi-step global processing. To do this, we need to define what global visual tasks entail. Unlike local tasks, which can be solved with a small set of pixels, global tasks necessitate a comprehensive understanding of the entire visual scene. For instance, in ImageNet classification, recognizing a small patch of cat whiskers can lead to classifying the image as a cat, highlighting the reliance on local features. Humans, however, do not depend solely on local information. For example, a driver must observe multiple objects and their behaviors in the environment, not just the view directly in front of the car. Studying complex real-world tasks like autonomous driving to evaluate model learning is impractical due to their complexity. Instead, we need interpretable tasks with clear data generation processes to assess reasoning abilities. To fulfill the need for visual tasks that require global multi-step reasoning, we propose 4 simple datasets, inspired by the connectivity task from the AI Winter. This task, discussed in the book, Perceptrons, demonstrated that single-layer perceptrons cannot distinguish figures based on connectivity due to their limitations. Our proposed tasks, including a graph connectivity task and a maze solvability task, require an understanding of connectivity. These tasks are global because knowing a small part of the graph or maze does not provide meaningful insight into the overall structure. We have also created visually engaging versions of these tasks, such as the strings task and circular mazes, to enhance their appeal. These datasets allow us to test both reasoning and visual recognition abilities, which is our main objective. Despite the advancements in modern vision models compared to earlier perceptrons, current models still struggle with global tasks. They can handle simple graph connectivity and maze problems, but their performance drops to random accuracy as tasks become more complex, regardless of model size or pre-training. To address this issue, we introduce the concept of visual scratchpads. Similar to scratchpads in text models, a visual scratchpad consists of frames that illustrate the reasoning behind a sample's label, such as showing a path in a maze. During training, the model learns with these scratchpads and must generate them during testing. The scratchpad guides the model in breaking down the global problem into simpler subproblems. Interestingly, we find that even a single-frame scratchpad, which only visualizes the final solution, significantly boosts performance, enabling the model to learn most tasks. The model exhibits a hierarchical learning behavior, gradually learning the solution during training. For multi-frame scratchpads, we propose a model that generates frames in a sequential manner, called the inductive scratchpad model. This model outperforms the single scratchpad model in both in-distribution and out-of-distribution settings due to its adaptive compute time and Markovian approach. Our work differs from previous efforts in textual scratchpads because visual data has unique characteristics. Unlike language, which consists of discrete tokens, vision deals with continuous inputs in a 2D space. This difference affects how models generalize to more challenging samples, as more objects can fit within the same pixel space without needing extra positional information. These features make vision a promising area for applying and expanding the scratchpad concept. In summary, our contributions include analyzing globality in computer vision to differentiate between global and local tasks, developing datasets inspired by foundational connectivity tasks that require global reasoning, and introducing visual scratchpads to facilitate multi-step reasoning in vision models. We demonstrate that a single-frame Scratchpad model can learn tasks that previous models could not, and we present a recurrent model for generating multi-frame Scratchpads that enhances generalization capabilities. Section Summary. In this section, we discuss the limitations of modern computer vision models in performing deep, global reasoning tasks, highlighting their reliance on local features and the lack of rigorous benchmarks for assessing global reasoning capabilities. We propose 4 new datasets inspired by foundational connectivity tasks and introduce the concept of visual scratchpads to enhance multi-step reasoning, demonstrating that these approaches significantly improve model performance on complex visual tasks. Section: Global Visual Reasoning Datasets. In this section, we discuss global visual reasoning datasets. Vision models have excelled in various tasks like image classification, segmentation, and object detection. However, these tasks share 2 main traits. Local features in images are often very informative, and humans can solve these tasks quickly without much thought. We can relate this to the System 1 and System 2 thinking. These visual tasks are typically handled by our System 1, requiring little to no complex reasoning. Not all visual tasks are straightforward, though. For instance, solving a maze requires more thought. When faced with a large maze, we often need to deliberate and trace paths to find connections. In maze tasks, local features do not provide enough information to determine connections, especially if we only have a few patches of the maze. To address this, we propose several visual datasets focused on connectivity. The first is the cycles task, where we randomly place nodes on a circle and connect them with edges to form either one large cycle or 2 smaller ones. Our goal is to determine if the graph is connected or not, which requires reasoning about multiple nodes. Next, we introduce the strings task, which involves random strings that can either be 2 closed loops or 1 longer loop. Here, the nodes are not visible, and the strings are created using smooth curves. The complexity can be increased by adding more invisible anchor points. We also consider a maze solvability task, where we have a start and an end point within 2 connected components. Our task is to determine if these points are connected. We provide both rectangular and circular versions of the maze to enhance visual complexity. For each task, we can visualize our reasoning process. In the maze, we might color cells starting from the source to see which areas are reachable, similar to a breadth-first search. For the cycles task, we can color nodes connected to a starting node, and for the strings task, we color one or both strings based on their configuration. We always start coloring from the rightmost node for cycles and strings. The visual scratchpad can be presented in a single frame or as a series of frames showing our progressive coloring. This mimics how we naturally approach these problems, starting from a point and expanding our search. Examples of these processes can be found in the figures and appendix of our paper. Section Summary. In this section, we introduce new visual reasoning datasets focused on connectivity, including tasks involving cycles, strings, and maze solvability, which require more complex reasoning than traditional visual tasks. These datasets are designed to challenge models by necessitating the consideration of multiple interconnected elements rather than relying solely on local features. Section: Globality, Locality, and Scratchpads in the Visual Domain. In this section, we explore the concepts of globality, locality, and scratchpads within the visual domain. We discuss how globality relates to visual tasks and connect the idea of a visual scratchpad to scratchpads used in text. Recently, the concept of globality degree was introduced to clarify why some tasks are challenging for transformers and to highlight the effectiveness of scratchpads in text. We define the globality degree of a task as the smallest number of tokens needed to provide significant information about the output. Specifically, for a set of input tokens and an output, the globality degree is determined by the minimum number of tokens that, along with their distribution, convey enough information about the target. We extend this definition to vision tasks handled by vision transformers, VITs. In our definition, we consider images divided into patches. The globality degree with a certain threshold indicates the least number of patches required to achieve a specific level of mutual information with the target. A higher threshold means the patches are more informative, and fewer patches are needed for the task to be considered less global. We aim to characterize which targets can be learned efficiently based on the number of patches. As the number of patches increases, we expect the learning complexity to depend polynomially on both the number of patches and the threshold level. Our focus is on a regime where patches are large enough that only one specific arrangement is valid, which we refer to as the significant patch regime. In contrast, when patches are small and constant in size, we need to adjust our definition to account for tasks that are permutation invariant, which may be easier for transformers to learn. A task being local means that a small number of patches can provide significant information about the target, but it doesn't imply that the task doesn't rely on all patches. For example, traditional vision tasks like image classification are often local, as a few patches can reveal important information about the class. However, our proposed datasets tend to be more global, where seeing only a few patches does not help in identifying the label. To support our claim, we conducted an experiment where we masked patches in a dataset and observed the model's performance. We found that while the model performed well on a standard dataset even with most of the image masked, it struggled with our more complex task when a significant portion was masked. This indicates that our task has a high globality degree, requiring more information to learn effectively. We also discuss the connection between visual scratchpads and those used in text. Scratchpads involve training models to generate intermediate reasoning steps, which can enhance learning. For instance, training models to first produce intermediate steps before arriving at a final answer has been shown to improve accuracy. In our context, Scratchpads can help reduce the globality degree by providing intermediate targets that are easier to learn sequentially. Each frame in a multiple frame Scratchpad can be seen as a low globality function of the previous frame, making it easier to determine the final label. Interestingly, even a single frame Scratchpad can lower the globality degree of a task. Learning from the complete Scratchpad is also a low globality function, allowing for weak learning that can lead to stronger learning through hierarchical methods. We will elaborate on this phenomenon in further sections. Section Summary. In this section, we explore the concepts of globality and locality in visual tasks, defining the globality degree as the minimum number of patches needed to achieve significant mutual information with the target label. We demonstrate that mainstream vision tasks are typically local, requiring fewer patches for learning, while our proposed tasks exhibit high globality, necessitating more information for effective learning, and we discuss how Scratchpads can help reduce learning complexity by providing intermediate reasoning steps. Section: Methodology. In this section, we outline our methodology for visual reasoning datasets, which includes 3 supervision formats: no Scratchpad, single-frame Scratchpad, and multi-frame Scratchpad. We utilize a vision transformer (VIT) backbone across all formats. For the no Scratchpad baseline, we provide the model with an image, and it must directly produce the label. We employ a VIT architecture with a classification token, and we use a linear layer on this token's features to generate label predictions. We train the model using cross-entropy loss on these predictions. However, as we will demonstrate later, this model struggles to learn from our datasets, prompting us to explore the single-frame Scratchpad next. In the single-frame Scratchpad format, we modify the no Scratchpad architecture. Here, the model predicts both the label and the complete Scratchpad image. We retain the VIT encoder with the classification token and add a linear layer to predict the Scratchpad image from the last transformer layer's hidden representation. During training, we apply cross-entropy loss for the label and mean-squared loss for the Scratchpad image. We will show that this model outperforms the no Scratchpad model and can learn the proposed tasks effectively. Next, we introduce our inductive model for multi-frame Scratchpads, which demonstrates superior performance in both in-distribution and out-of-distribution settings. In this model, we predict each Scratchpad frame sequentially, relying only on the previous frame or the initial input image. For instance, We first predict the first Scratchpad frame using the input image, then use that frame to predict the next one, and continue this process. The model includes a recurrent component that takes an input image or a Scratchpad frame and predicts the next Scratchpad frame, the label, and a halting signal. This process continues until the halting signal is activated or a maximum number of recurrences is reached. The final label prediction comes from the last recurrence, and importantly, each frame generation depends solely on the last generated frame or the input image, without retaining any history. During training, we initially used teacher forcing, providing the model with perfect frames from the training set. However, this led to discrepancies during inference, as the model would then use its own generated frames, which might differ slightly in distribution. To address this, we implemented an alternating training procedure where the model sees perfect frames half the time and generated frames the other half. This approach helps the model learn to manage imperfect inputs, enhancing its performance during inference. In the experiments section, we evaluate the performance of various methods on our datasets, focusing on model size and out-of-distribution generalization. Each dataset contains 1 million training samples. For model size experiments, we compare the performance of different methods with varying model sizes, including the no Scratchpad baseline, the single-frame Scratchpad model, and the inductive Scratchpad model for multi-frame predictions. We test 4 sizes of the VIT encoder: small, base, large, and huge, with approximately 22 million, 86 million, 307 million, and 632 million parameters, respectively. The results show that the no Scratchpad baseline achieves only random accuracy, while the single-frame Scratchpad model learns certain tasks with larger models. In contrast, the inductive Scratchpad model successfully learns all proposed tasks, even with smaller models. We note that the parameter counts for the 3 methods are quite similar, with the single-frame model adding only a linear layer for Scratchpad prediction and the inductive model adding a linear layer for the halting signal. However, the inductive model's inference time can vary based on the complexity of the sample, often resulting in longer computation times compared to the baselines. Section Summary. In this section, we describe our methodology for visual reasoning datasets using 3 supervision formats: no Scratchpad, single-frame Scratchpad, and multi-frame Scratchpad, all utilizing a vision transformer, VIT, backbone. We demonstrate that the single-frame Scratchpad improves performance over the no Scratchpad baseline, while our inductive Scratchpad model for multi-frame predictions shows superior results in both in-distribution and out-of-distribution settings, employing an alternated training procedure to enhance robustness during inference. Section: OOD generalization. In this section, we examine the out-of-distribution, OOD, generalization performance of various methods, highlighting that the inductive Scratchpad model excels in this area. This advantage arises because the inductive Scratchpad model focuses on learning the reasoning steps, making it adaptable to more complex problems without being limited by the number of steps needed. For the cycles task, we manipulate task complexity by varying the number of nodes. Specifically, we train on samples with 12 nodes and test on samples with a greater number of nodes, increasing complexity. We visualize these results in a figure. For the maze tasks, we maintain a consistent maze size to avoid resolution issues. Instead, we create a simpler training dataset, where the distance between connected source and sync points is 30 or less, and use the main task dataset for validation. We provide further details on the OOD training datasets for the maze tasks in the appendix. The OOD results for the rectangular maze task are summarized in a table, showing that the inductive Scratchpad model achieves nearly perfect accuracy on OOD samples, while the single Scratchpad model performs slightly better than random guessing. We include additional OOD experiments in the appendix. Next, we explore related literature from various perspectives. In recent years, the reasoning capabilities of neural networks, particularly transformers, have been studied across different topics, from synthetic symbolic datasets to algorithmic tasks and natural settings like mathematical reasoning. These tasks often involve complex combinations, leading to a vast input space that makes memorization-based learning impractical for transformers. To evaluate the reasoning abilities of neural networks, we can test their OOD generalization performance, determining if they rely on superficial cues or can apply learned rules to more complex OOD samples. A specific challenge in OOD generalization is length generalization, where models struggle to generalize to longer instances than those seen during training, even in simple arithmetic tasks. This difficulty increases when the input or solution length exceeds what the model has encountered, leading to significant variations in performance based on the use of different positional embeddings. While there has been progress in understanding reasoning in symbolic domains, visual reasoning research has often focused on simpler reasoning types, emphasizing image semantics. However, visual tasks provide a solid foundation for OOD and length generalization experiments, as we can create more challenging examples without changing image resolution. Various datasets have been developed to assess different aspects of visual reasoning. For example, the Visual Question Answering (VQA) dataset poses questions about images in natural language, requiring an understanding of image semantics and basic reasoning. The CLEVR dataset is a diagnostic VQA dataset featuring synthetic objects that eliminate misleading correlations found in traditional datasets and clarifies the types of errors models can make. Reasoning operations in CLEVR include counting, comparison, and attribute identification. The GQA dataset, which uses real images, focuses on answering compositional questions inspired by CLEVR. The VCR dataset emphasizes common sense reasoning, asking deeper questions based on images. CLEVR-ER examines video understanding with CLEVR-like objects, while the Cater dataset focuses on temporal reasoning, tracking objects in videos. Aker assesses vision models' performance in causal induction, and the Winneground dataset tests compositional reasoning by matching images and captions. Other datasets, like the FIRE dataset, require reasoning with physical world models. Most of these datasets depend on understanding image semantics and are generally easier for humans to solve compared to our proposed datasets. The MathVista dataset targets mathematical reasoning in a visual context, combining images and text, but the reasoning is primarily text-based. Some datasets draw inspiration from human IQ tests, but it remains unclear how to increase their difficulty and reasoning requirements. The Pathfinder dataset demonstrates that convolutional neural networks struggle with long-range spatial dependencies, and it was later included in the long-range ARENA benchmark to evaluate transformers' ability to model these dependencies. Our datasets, however, focus on the overall complexity of the task and the number of reasoning steps needed, and we believe they are unique in offering a scalable degree of globality and reasoning challenges for humans. Section Summary. In this section, we analyze the out-of-distribution OOD generalization performance of various methods, highlighting that the inductive Scratchpad model excels due to its ability to learn reasoning steps independently of their quantity, enabling it to tackle more complex problems effectively. We also review related literature on reasoning capabilities in neural networks, particularly transformers, and discuss various visual reasoning datasets that assess different aspects of reasoning, emphasizing the unique challenges posed by our proposed datasets. Section: Scratchpad and Chain of Thought. In this section, we discuss the concept of scratchpads and chain of thought reasoning. We introduced the idea that training transformers to produce intermediate reasoning steps, alongside the final answer, can enhance their performance on reasoning tasks like arithmetic, math, and code understanding. We found that models can learn to reason step by step by observing just a few examples, which we refer to as chain of thought, COT. Subsequent research demonstrated that pre-trained language models can generate these chains of thought simply by being prompted. We provided theoretical insights into why scratchpads are effective, using the concept of globality. Additionally, we introduced a variation called the inductive scratchpad for multi-step reasoning, which employs a dynamic masking technique to focus only on the input question and the last reasoning step, leading to better performance in generalizing across different lengths. Recently, there have been attempts to apply the visual aspects of scratchpads and COT in multimodal models. For instance, visual COT takes an image and a question as input, first predicting a bounding box around potentially relevant information in the image, then concentrating on that area to improve the answer. This approach is particularly useful when the answer is found in a small section of a high-resolution image, like tiny text in a corner. However, this work does not tackle complex reasoning tasks that require multiple steps or generate images as Scratchpads or COT. We also note concurrent work introducing the concept of Sketchpads, which utilize visual operations and tools, like drawing lines and bounding boxes or using Python for plotting, to create sketches that aid reasoning for questions with both text and visual elements. The key distinction in our work is our focus on visual tasks that require multiple reasoning steps and have a high degree of globality, while their approach does not address such complex visual tasks. Our perspective is to use visual Scratchpads to make tasks more learnable, whereas their method relies on tools to create images that guide the model. Furthermore, our models can generate a sequence of frames representing reasoning steps, with each image created freely by the model. In contrast, the Sketchpad method can only produce a single sketch using a limited set of predefined tools and operations. We also highlight that several studies have integrated recurrent components into transformer architectures. Notably, universal transformers share weights across layers and adaptively vary computation time by changing how many times a layer is applied. We emphasize that our proposed inductive model is much simpler than these architectures. This simplicity arises from the Markovian nature of our Scratchpad frames, which means there is no adaptive computation time during training. Instead, the model is trained to generate the next frame based solely on the current frame, without considering any previous history. Additionally, the halting mechanism is supervised during training.